Hello, ladies and gentlemen. Today we're going to be talking about how to write an equation of an exponential function. So if you remember just really quick, an exponential function is a function where x is in the exponent and that base or that b is either a growth factor or a decay factor depending on if it's greater than 1 or less than 1. So we're going to actually be given either a table, a graph, or a situation about an exponential model, and then we're going to write the equation for that either situation, graph, or table. So what you're going to need today is your foldable, a writing utensil, or a calculator. Calculator is kind of optional, up to you if you like working with a calculator or not. Okay, you do not have to write this in your foldable, but let's review really quick. When we've been given a table and we want to figure out the function, we typically find the pattern that's happening within the x's and within the y's. So from 2 to 3, I added 1 in the pattern. And to get from 3 to 4, I added 1. To get from 4 to 5, I added 1. To get from 5 to 6, I added 1. And 6 to 7, I also added 1. So my pattern in the y's, how do I get from 5 to 8? Well, I'm going to plus 3. Well, what about 8 to 11? Oh, I'm going to plus 3. And 11 to 14, I'm still adding 3, adding 3, adding 3. So when this happens, if you're adding or subtracting a constant number or a number that's the same every single time, the type of function that you have is linear, or it's going to be a line because our change in y over the change in x is going to be 3 over 1. So I have a constant rate of change or slope of 3. Okay? So what if we did that to this set of this table or this set of ordered pairs? So to get from my x's from -1 to, or -2 to -1, excuse me, I'm still adding 1, adding 1, adding 1, and I'm adding 1. But now when I go in my y's to get from 7 to 3, I'm subtracting 4. To get from 3 to 2, I'm subtracting 1. And then to get from 2 to 3, I'm adding 1. And then to get from 3 to 7, I'm adding 4. Well, it's definitely not linear, but what other types of graphs, if you think way back to first semester, what other types of graphs did we learn in Algebra 2? Well, we learned ones that are U-shaped, right? So that would be this pattern because we have a 0, 2, and we have a -1, 3, 1, 3, and then 2 all the way up at 7, and -2 all the way up at 7, right? So the type of function that we have with this pattern, where we see that it's symmetric or making a U shape, is a quadratic, or what we also call parabolas, right? So today we're not going to talk about linear or parabola functions, parabolic functions, but we're going to talk about exponential functions. And we know that the exponential function's generic form is this, right? This is the last thing that we learned on how to graph exponential functions. And we knew that a, h, and k all meant transformations on my parent function. But what if we take away some of those parent or those transformations on the parent function? If we take away moving left or right or up and down, all we're left with a stretch or a shrink on that parent function, where our parent function is y is equal to b to the x. The most basic an exponential function can get is some number getting raised to that x power. Okay, so and then today when we write exponential functions, we're going to be talking about the a value when we're writing them from a given situation. All right, so example number 1, we need to write a function for the table provided. So we've been given a table, and just like we did on the first 2 examples that we didn't write in our notes, we're going to find a pattern. So now that you see the little pencil on your slide, you can start writing in your notes. So in my y column, how I'm getting from 5 to 15 is I'm multiplying by 3. And 15 to 45, I'm still multiplying by 3. And from 45 to 135, I'm still multiplying by that constant value of 3. So I know that my function has to look like this. Y is equal to some number times some number raised to the x power. So I have to figure out what a and b are for this table, okay? Well, if I'm multiplying by 3 every single time, each time I put in an input, my value is getting tripled. So that means that this number that you're multiplying by is always going to be your base number. So that means that 3 is getting raised to the x power because each time you're multiplying by 3. Just like if we say we have 3 to the third power, we're multiplying 3 times 3 times 3. So now depending on what input value I plug into my function, I'm going to take 3 to that power. Okay, A is going to represent our starting value. So A is always going to be what our y value is when x is 0. It's not when x is 1, so it's not 15, and it's definitely not anything else, but our starting value means our y value when x is equal to 0, okay? So in this case, that would be 5. So my final answer is y is equal to 5 times 3 to the x. That's my final answer for the function for this table. I just wrote the equation of the function according to this table. Okay, example number 2. So for some exponential function of the form f of x is equal to a times b to the x, it's given that when we plug in 2, we get back a value of 96, and when we plug in 3, we get back a value of 384. So just like on example number 1, you guys, for every situation that we've been given, if they don't give you a table, make sure you write the table in your notes, okay? So I don't think your foldable has a little table for you, so you want to write that in. So we need to figure out what our a and b are in our equation, right? So so my general form is y is equal to a times b to the x. And so I have to figure out what A is and what B is. Well, I have to figure out what I'm multiplying by. So what am I multiplying by to get from 96 to 384? Well, if I take 384 divided by 96, that tells me that I'm multiplying each time by a factor of 4. So that means my B value is going to be 4 to the x. But I still need to figure out what my value is when my A value is when x is 0. So that means that I have to work backwards. So to get from 96 to 24, I had to divide by 4. And then to get back again, if I divide by 4 again, I know that 24 divided by 4 is 6. So I had to work backwards to figure out what my A value was when x is 0. So that means that my A is 6. So my final answer is y is equal to 6 times 4 to the x. So if they don't give you that A value, you have to work backwards to figure it out. Okay, example number 3. We have been given the graph of f of x, and we need to write the equation of that graph in the form f of x is equal to a times b to the x, or y is equal to a times b to the x, okay? So just like I said on example number 2, if they don't give you a table, we need to make a table, okay? So make sure you write this table in your notes. So they told me for an input value of 3, I get back 189, and for an input value of 5, I get back an output of 1,701. So if I take 1,701 and divide it by 189, I get back 9. So to get from the input of 3 to the input of 5, I'm multiplying by a value of 9. But that doesn't help me. I want to figure out how I get from 3 to 4 or from 4 to 5. So I have to figure out what I'm multiplying by here to figure out what my B value is. Because I need my A value, my starting value, and my growth factor. So what am I growing by on each step of my table? Well, I know 2 steps are a value of 9. So what if I half that? What if I try doing 189 times 4.5? Well, that gets me 850.5. And if I times that by 4.5 again, that gets me 3,000, which isn't what we have for our step 5. So I know that if I multiply by 3 and then 3 again, that's the same thing as multiplying by 9 for 2 steps. So my growth factor is actually 3, because your growth factor or your B value, you guys, is if we just go from one entry to the next in our table in our Y column. So from here to here, or from here to here, or from here to here. It can't be 2 steps or 2 distances in our y column, okay? So I have to work backwards now. So I have to figure out what 1701 is divided by 3. That means that when I plug in 4, I get back a value of 567. And then if I keep going and I work backwards to this 0 value, I'll figure out what my a is. So if I take 189 divided by 3, I get back 63. And if I divide that by 3 again, I get back 21. And if I divide by 3 again, I'll get back 7. So that a value is going to be 7. So my function is y is equal to 7 times 3 to the x. Hopefully that makes sense. If you guys have questions about this part of the process, please, please, please ask me in class if you didn't understand that part of the notes, okay? Okay, we have one more example. We have a zombie virus that's growing at an exponential rate, and we know that after 2 hours we have 1,120 zombies, and after 6 hours we have 286,720 zombies. So our first part of this problem is to determine the equation that models this population exponential growth, okay? So we're growing exponentially. So we know that b is going to be greater than 1 because we have a growth problem. So let's make a table from the information that we know. We know that if we've been given 2 hours, we have 1,120 zombies, and 6 hours, we have this many zombies, okay? So we have to figure out what our growth factor is from each step, and we still have to figure out what our a value is when x is 0, okay? So we know that from 1,120 to 286,720, we're multiplying by 256. And I found that out by just taking 286,720 divided by 1120 is 256. Okay, but that's 1, 2, 3, 4. So that's 4 times that I'm multiplying. So when I go from hour 2 to hour 6, I'm multiplying by 256, but that has 4 steps in between it. So we have to figure out what we're multiplying by on each one of these guys before we figure out our growth rate. So remember last time when we had 9 and then 2 steps and we figured out it's multiplying by 3? So if we have 4 steps, because ultimately what we're doing, you guys, is we're trying to figure out how things are growing exponentially. So the opposite operation of an exponent is a root. So I have 4 little arrows or 4 steps that I'm trying to figure out. I'm going to take the 4th root of 256 and I get back 4. So let's try that. So if I take 1,120 and multiply it by 4, I get 4,480. And if I multiply that by 4, I get 17,920. So if I multiplied that by 4, and if I multiply that by 4, I get 71,680. And if I multiply that by 4, I get back the 286,720. So in order to figure out our growth factor when we've been given more than one step in between, you're going to have to take a root of how many steps that you're missing. So to get from 2 to 3 and 3 to 4 and 4 to 5 and 5 to 6, we have to multiply by that growth factor of 4. So if we're working backwards to 0, we're going to divide by 4. So we need 1,120 divided by 4 is 280. And if we take that divided by 4, we get back to 70. So my starting value is 70 and my growth rate is 4. So that is the equation that models this growth rate of the zombie population, okay? So zombies are quadrupling every single hour, and we started with 70 zombies. Okay, so the last bit I just said on the last slide is going to help us figure out part B and part C. So what is the significance of the A value in the context of this problem? It's the beginning number of infected people. So we started with 70 people who were infected. Okay? And then part C, what is the significance of the B value in the context of this problem? My B value is always going to be my rate at which I'm, in this case, growing, but sometimes you can be declining. So like if we're talking about carbon dating as something that decays over time, my B value is going to be at the rate at which it's declining. But for this, since our zombies are growing, my B in this problem is going to be the rate at which my zombies are growing. Okay, so that's all I have for you in your notes today. So I want to thank you all for taking such good notes, and I'll see you soon. If you have any questions about the tables from the last two problems, example 3 and 4, please, 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 please ask me in class. All right, bye.